Hello. So I work at Ambiata, and we use simple models to predict the future. And this is my boss with his eyes closed. And when he opens his eyes, he tells me that the thing about these simple models is that they need an enormous amount of data in order to be predictive. And this puts us in an interesting position that it costs a lot more to process this data than it does to build the processing tools. So it's worth spending some more time on development so that we can cut down on operational costs. So what does this mean? What are our options? Does it mean that we're back to this? Are we going to resort to the so-called king of performance per dollar in order to get our operational costs down? Do we have to leave the comfort of our warm, fuzzy functional languages and go back to the semicolon mines? Well, unfortunately for us, or perhaps fortunately, correctness is our #1 priority. And C++'s mutable state and manual memory management is just not a good fit. Our customers pay us to make accurate predictions. And if we screw up, it's not just a bad day. We could lose a customer. So what's a developer to do? Well, we're here at a functional programming conference. So we take our favorite industrial strength programming language, our favorite industrial functional language, and we do what it does best. We build a domain-specific language, one that's expressive enough to be able to describe all the kinds of queries that we want to do over this data, but it's restricted enough so that we can guarantee efficient execution. But then the key to delivering on this promise is that we build an optimizing compiler. A compiler that produces the kind of C code that you would never want to write by hand, but that runs crazy fast. And for Ambiata, that means Icicle. Icicle is a query language for time series data, and it guarantees with its modal type system that queries are restricted to just a single pass over the data. In case you weren't here for the last session, this is what an Icicle query looks like. Here, we're taking the last 5 values from some time series, and then we're going to compute the mean of those last 5 values. So how do we go from this source? So this source code now will go through a number of transformations before we can produce efficiency. So how do we get from the icy mountaintops down into the deep sea? Well, there's a lot more that I can cover in half an hour, but I'm going to tell you about 3 optimizations that we found particularly effective in our journey from source to sea. Schema specialization, partial evaluation, and data flattening. So let's start with schema specialization. I often hear developers say that their code's I/O bound, and I find that really hard to believe. When you say it's I/O bound, all I'm thinking is it's 1996. This is the year the Quantum Fireball was released. 5,400 RPM, 7.6 megabytes per second of glorious spinning Rust. Now, let me share with you the reality of 2016. Just before I left the hotel, I benchmarked this laptop, and it managed to crank out 1,800 megabytes per second sequential reads. So if I combine that with the 2.5 gig processor, that gives us about 1.3 cycles per byte if we want to keep up. What can you do in 1 cycle? You can multiply an integer, that's about it. I had a look online, and the fastest hard drive I could find goes at 3,300 megabytes per second. It's only 0.7 cycles per byte. So things are not getting better. And you're going to have to work extremely hard if you want to max out today's hard drives. So let me tell you, you're not I/O bound. Your code is just slow. So where do we start? If you want the performance of the rest of your code to even matter, then you need to get the bytes off disk as fast as possible. Now let's look at a concrete example. Most recently, I needed to parse this format. It's the one true enterprise format. with some Web 2.0 for good measure. And the point that I want to focus on is that to achieve good parsing performance, you must avoid reading one byte at a time. You need to read multiple bytes at a time. So how can we do that? Well, because Icicle queries are compiled on demand right before we're going to run the query, and we've got the expression and we've got the schema for the code that we're going to be processing, we can tailor our parser exactly to the expected input. And that means we can take full advantage of what we know to generate the perfect parser. So what do we know? Well, in this case, we know that the row cannot contain a line feed. And we also know that these first two columns can't contain a pipe. And that means we can find the locations of 3 of our separators very quickly using memchar. Good implementations of memchar will use SIMD instructions to scan multiple bytes at a time. And this is critical to good parsing performance. If you're not building a compiler and you just want to be able to use this, you can get access to it in Haskell with byte string lmindex. So you might have noticed we missed the third pipe, and why is that? Well, the JSON here on the third column might contain a pipe, so we can't just scan past it. But we can use what we know to do something even better. We know that the date's exactly 10 bytes. So we can scan backwards from the line feed and locate the pipe. We've got our separators located without resorting to single byte scans. So what about the contents of the columns? Well, this second column has a well-known schema, as does the third, and we know that for this JSON blob, we know all the possible properties and what their types are. So how does this help? Well, when we're proceeding with parsing, we need to compare these strings. But we could compare them one byte at a time, or maybe we can just pretend that they're integers. Or perhaps strings are just 32 or just strings with 32 or 64-bit characters. In Icicle, constant strings are compared as though they're composed of 64-bit characters. So let's look at some real generated C code. So this has actually come out of the Icicle compiler, and here we're reading this adjusted close property. And the astute in the audience might notice that we're doing unaligned reads. But we're only working on Intel, so this is fine for us. So here we're comparing the first 8 bytes as a 64-bit int, and that's the adjusted part. And then here we're comparing the last 6 bytes, and that's the underscore close part. And you'll notice that we have to mask out the bytes that we don't care about, and we always pad our buffers with an extra 8 bytes at the end so that this is safe to do. Remember, always read multiple bytes at a time where possible. This is our best weapon for increasing parsing performance. Okay, so we have our data loaded into memory without breaking the bank. How are we going to optimize its evaluation? One avenue for optimizing expressions is a technique that we like to call partial evaluation. And the idea is just to evaluate as much of the expression as possible at compile time. And for us, we're going to use a combination of beta reduction and constant folding, which we'll talk about later. It's also a side benefit of this to us is that we would like to get rid of any lambdas that we have in our intermediate representation so that we don't need to compile them to C. Now, you might be thinking, don't GCC and Clang and LLVM do this kind of thing already? They do attempt to do this, but they need to worry about aliasing and phi nodes and inter versus intra procedural optimization. And given these hazards, they do an amazing job. But we're working at a much higher level. The Icicle is a pure and total language, and because of this, we can just keep evaluating and evaluating until there's nothing left. We don't need to worry about evaluation diverging. So let's talk about beta reduction. Beta reduction you can kind of think of as inlining, I suppose. And it's the result of applying a function of calculating the result of applying a function to an expression. So here we have a lambda applied to the literal 9, and we want to beta reduce this. So you can see the lambda has an argument x, and x is used just once. So we're going to substitute 9 for all occurrences of x. So we do that. And then we're going to replace the whole expression with the body of the lambda. And that's beta reduction. Constant folding is the evaluation of primitive functions applied to constant arguments at compile time rather than runtime. So we go back to our example. We can see we've got the primitive add applied to 2 constant arguments, so we can evaluate them at compile time. Let's take a look at a real example. Now, you might imagine writing some of this Icicle code. And after Icicle parses this source, the first thing it does is inline everything and smash everything together. So we're going to do that. So bar gets inlined here, and then foo. And then we end up with something that might look a bit like this. So you would obviously never write something like this yourself, but this might be something that Icicle gets after inlining. And then we translate this to Icicle core. And so those case analyses have become folds over the data type because we don't have case expressions in core. It's just very simple kind of lambda calculus. And this is where we begin our partial evaluation. So one thing that's interesting to note is that fold either and fold maybe can't be beta reduced because they're primitives. So we switch to constant folding, and the Icicle partial evaluator moves bottom up, so that means we're going to be touching the leaves of the AST first. So we find this and constant fold it into 65535. Now you might think that there's no more opportunities for constant folding, but actually if we look at this fold maybe.
Didn't you say 2 to the 16?
Yeah.
This is an odd number.
Anyway.
Okay, sorry.
Yeah. So if we look at this fold maybe, we'll see that the first 2 arguments are actually constant expressions, and that we know just enough about the third argument to be able to evaluate it. So we can do that. So you can see we're left with the lambda, which was the second argument, applied to the third argument, but with the just peeled off. So now we go back to beta reduction, and we notice that, so we try beta reduction again, sorry. We find this lambda applied to an expression. So we beta reduce it. Back to constant folding. Again, we know we have just the right information. So we can constant fold that. Back to beta reduction, and we're done. So you can see we've applied beta reduction and constant folding in tandem, and we'll be able to evaluate a bunch of our expressions, get rid of heaps of code, and we have no lambdas left, so it's easy to compile to see. Because we're working at a higher level, we can evaluate things that are well out of reach for GCC, Clang, and LLVM. So onto our final transformation, data flattening. And the general idea here is that we want to melt down our data types into primitives so that we can get better memory locality, and also so that it's easier to compile to see. In fact, initially we just did this transformation so that it would be easier to compile to see. And if we'd taken, if we had decided to not do this, we could have taken an alternative approach. So you can see here we've got a data structure price with high and low, and we could have just converted this to a C structure. But then when we come to maybe price, we have to generate these sort of concrete combinations, and that could be a problem for polymorphic types. You can imagine either, and like maybe we have some user data types, and we just don't want to generate every single combination of these polymorphic types smashed together with the concrete ones. One option would have also been to use templates, and this would have alleviated the problem with polymorphic types. But we really didn't want to use C++ as an intermediate language. I tend to feel that if we had switched to C++, we might have been tempted to push more and more of our more and more of our complexity down into the high-level abstractions that C++ offers, and then we would not have had a really good idea what kind of assembly we were going to get at the end, like we do with C or LLVM. Now, not everyone in the audience agrees that this was a good idea. And in fact, while we were working on this transformation, it was turning out to be quite tricky, as we'll see at the end, to get right. And I was off sick one day. And I come back the next day, and the back end has been converted to C++. Now, let me tell you, there is not a single thing on this earth that will motivate you to finish a piece of code quicker than the threat of C++. So along the way, we were surprised to find that transforming our data types in this way not only makes it easier to compile to C, but it also exposes some additional optimization opportunities. And you also get very nice memory locality for your array access. So let's talk about melting data. Before we try to apply this transformation, I want to show you how we're going to melt down our data types, and then we're going to explain the two primops that are going to help us do it. So if we've got this data type price with open, high, and low, if we imagine that you have a variable of this type price, then we're going to melt this variable down into 3 variables of open, high, and low. It's easy enough. If we have maybe price, then we want to melt down this into 4 variables is just open, high, and low. Now this is where it gets interesting. If we have an array of maybe price, then we're going to melt this down into 4 arrays. And this is where we get our nice memory locality. So let's talk about unpack. This is the type of unpack. It's a bit crazy, sorry. The curly braces here are just to sort of denote arguments which are going to affect the shape of the rest of the type. So here we're taking an index and a type and then a value of that type. And then we have this final thing, which is a bit funny. So we want to melt down the type. We want to melt down a value of that type. And that's going to give us back a list of the types that are melted, similar to what we've seen on the previous slides. And then we want to index into that list to pull out the type that we need for our return type. This might make more sense if I show an example. So here, if we got unpack 0, take 0, and then the type maybe price, and then it gives you back a function from maybe price to bool. And then for the other indexes, we get back functions to extract those. Now let's talk about the opposite of unpack, which is pack. And that's going to take the components of a value and smash them back together into a full value. So this is the type of pack, a bit simpler. It takes a type, and then it takes this melting thing again, which will figure out what are the types in its melted form. And this is a bit of a lie, because actually this is going to become carried function arguments, as we'll see, and it returns our value. So here's an example. It looks a little bit like if you were to construct maybe price all at once. So we got bool, int, and we get a maybe price. So let's look at a real example. Here we've got an Icicle program which takes the latest 5 values from some stream of prices, and then it's going to sum up all of the high values. This probably doesn't really make sense, but maybe you're going to do this on the way to calculating a mean or something like that. So this Icicle source is going to go to core, and then it'll go to avalanche, which is an imperative, simple imperative language that we use right before we produce C. So this is avalanche. And you'll notice that it has this sort of weird buff type. This is a circular buffer, so it's a bit like an array, but the size 5 is statically known at compile time, and that corresponds to the latest 5 in our original program. So we're going to initialize this mutable variable buff with an empty circular buffer. Then we're going to loop over the prices. So when we said that it's limited to a single pass over the data, this is the single pass. And we're going to push all of the prices onto this circular buffer. So you can imagine that the oldest ones will fall off the back and we'll be left with the latest 5. Then we're going to initialize an accumulator and read out the value of the buffer, and then loop over and just add up all the prices for hire. Just here. So now we know what this does. We're going to perform data flattening on it. So I'm going to move it over here to give me more space, because things are going to get a lot worse before they get better. I'm sorry if you can't read this, it's the best I can do. So we're going to start by inserting the pack and unpack primitives and flattening out and melting, the avalanche instructions. So we're going to proceed top to bottom. We find this buffer initialization, and it's initialized with an empty buffer of prices. So we're going to, so we notice that this is a compound type, it's not a primitive type. So we melt that down into 3 mutable variables. And the type of this empty thing is actually still buff5 price, and it's just that we're unpacking it. So we now have buff5 int, which is the type that we want for the variable. We come to the for loop, and we melt price into, we come to the for loop, and we melt price into open, high, and low. And because price was a pure variable in scope, I suppose, that's been bound, we now need to go and substitute in the rest of the program for price. So we find this one, and we replace that with a pack. So we repack open, high, and low. Now we find the read, we melt that. These names came from here, so there is some sort of naming scheme to make sure that things match up. Then we come across this, So now we've got rid of x's, and that was a pure value. So now we have to repack this x's. So we do that. I'm just going to move these out of the way because I'm going to run out of space. So these will come over here. And then I'm going to move the push over here. And we're going to melt the right. So that becomes 3 rights. And we have to unpack the buffer that we had just pushed onto. And you'll notice a pattern here that every time we melt a read, we go and substitute for a repacking of the values that we melted out. And every time we melt a write, we replace the payload of the write with an unpack. So let's move on. We hit read, so we melt that, and that means we need to substitute. So we find y's, and we pack that. So what was the point of all that? We seem to have just generated a huge pile of extra code. But you'll notice that by inserting the calls to pack and unpack, we've been able to sort of flatten and melt all of the avalanche statements. And at the end of all this, it still type checks. So that's really useful. It means that we don't have to do this transformation all in one pass, and so it's easier to get right. So now we're going to try and get rid of all of these pack and unpacks. So we go back to our original code, and we find these 3 buffers at the top, and we notice that we're just unpacking an empty buffer, so we can get an empty buffer of int. So we can just replace those with an empty buffer. Now we come down to here, and we notice that we're doing this dance of packing and unpacking only so that we can push the next value onto one of the buffers that we've read. So we can just replace those with pushes onto the relevant buffer. And then finally, we find this pack where we're packing together a compound buffer only so we can index into it and pull high out. So we get rid of that and replace it with just y's high. So now all the calls to pack and unpack are gone, and we're just left with primitive types. So much better memory locality, and it's going to be easier to compile to C. But what's interesting is we've exposed some optimization opportunities here. In our real compiler, we saw opportunities for common sub-expression elimination, but here I'm just going to show you some dead code. So go back to our example. We could see that all of this rubbish is unused. Everything to do with open and low, we're not using anymore. So we can just get rid of it. And now we have pretty much the same program that we started with, except instead of working over compound prices, we're just working over high. And What's even more interesting is that we're only using high in this loop, so we could feed that back into the parser and just skip over fields that we don't plan to evaluate anyway. Now, I think I need to come clean a little bit and say that it was probably a mistake to implement this in Avalanche. It's pretty horrible, all of these mutable variables and everything, and we probably should have implemented it in core where optimisations are easier because everything's pure and lovely. But we didn't really realize it was going to be so useful as an optimization enabler. So what's a performance talk without benchmarks? I just want to give the buckets of salt. These are really, really silly benchmarks. They're not even on big data. Maybe ask me after July or something for that. But maybe they give some kind of idea of progress. So the first one's just sort of demonstrating the parsing speed that we can do. So we just have one query in here, which is calculating the mean of some of the stock prices that you might have seen at Amos's talk. And here we're just grepping for an empty line. I should say that these like grep and WC, they're the ones off my MacBook, so probably the GNU ones are a lot faster as well. But yeah, the grep over this 60 gig file took about 13 minutes, I think, so it's 74 megs. WC minus L was 1:20, and we managed to do that and parse the JSON and calculate a query and output a result in less than a minute. So you can see we're getting close-ish to the upper bound, which is kind of cool. Now the next thing is kind of ridiculous, a bit more unfair, but it's a real world thing. So we have some R code that runs in production. And it's doing some real work for a customer over about 360 gig of data. It takes about 15 hours for it to calculate something like 400 queries. So with the fusion that Amos talked about, the fact that we're able to smash it into one query with the fast parsing performance, we can do the same thing in 11 minutes. And Mark's happy because less CPU time. Someone once compared C++ to building an octopus by nailing legs onto a dog. So if you're not into veterinary surgery, and if performance matters, you can afford to write a compiler. You can build a domain-specific language that hits the sweet spot for expressing your problem, but restricted enough such that it's efficient to execute. You can process multiple bytes at a time and maximize your I/O throughput. You can work at a higher level and do the kinds of optimizations that LLVM can only dream of. You can melt your data down and expose great memory locality and additional optimization opportunities. When performance matters, you don't need C++. You can do it all today in Haskell. Thank you.